For topic two, we're going to look at graphing systems of linear inequalities. So in the previous video, we talked about just what is a linear inequality in two variables. We reminded ourselves how to graph that. So you need to remember that when you're graphing a linear inequality in two variables, you're graphing the solution. That's how we solve these inequalities in two variables. We get a graph, okay? The graph is a visual representation of all of the ordered pairs that satisfy that inequality. So what is the solution? Well, when you're dealing with just a linear inequality in two variables, the solution can be the points on the line or not, depending on the type of inequality symbol we have. And then you have one of the two half planes. That's the solution to a linear inequality in two variables. So when we're dealing with a system of linear inequalities in two variables, we have two or more inequalities that we must satisfy simultaneously, or sometimes you'd probably be more likely to see it is that a system of linear inequalities in two variables consists of two or more inequalities that must be solved simultaneously. Okay? So, what does that mean? What is the solution to a system? Well, we know the solution to a single linear inequality in two variables is the points on the line or not, again, depending on the inequality symbol, and then it's one of the two half planes. Well, when you're dealing with the solution to a system of linear inequalities, it's still just the set of all ordered pairs x, y that satisfy the inequality, but like, what does that mean? Well, it's the area where the two shaded regions overlap. So basically what we're going to do for a system of linear inequalities in two variables is we're going to graph both inequalities in the same Cartesian plane, and we're going to see where the shading overlaps, okay? So that's kind of the question you ask yourself. Where does the shading overlap? And if you kind of think about that, that should sort of make sense. So let's go back to just a system of equations. So if we're dealing with a system of equations, we're looking for where those two lines cross each other. Where do those two lines intersect? Where is that point where the lines overlap each other? That's the point of intersection. That's the solution. So when you're dealing with inequalities, you no longer have a single ordered pair solution. You're going to have infinitely many ordered pair solutions, but they're a very specific set of ordered pairs where the shaded regions for each individual inequality overlap. Okay, so how do we do this? All right. So steps to solve a system of linear inequalities. The first thing we have to do is shade each inequality on the same coordinate plane and then shade the region that satisfies each inequality. So let's kind of just do a quick overview of what that entails. So the first thing we do is we solve each inequality for y. Okay, we want to put them in kind of like the equivalent of slope-intercept form. Okay, we want to plot the y-intercept and apply the slope. Okay, so just like we were dealing with a linear equation in two variables or a single linear inequality in two variables, we want to solve for y, put it in slope-intercept form, we want to plot the y-intercept and then apply the slope, and then we connect the points. And when you're dealing with inequalities, you have to be careful. You want to connect the points, but we have to be very particular. So if we have a strict inequality, plain old less than, plain old greater than, we connect with a dotted line. This tells the reader that the points on the actual line are not part of the solution set. So this boundary line, if you have a less than or just a greater than, the points on the line are not part of the solution set. And we indicate that with a dotted line. Now on the flip side, if you have less than or equal, greater than or equal, so those or equal to inequalities, we would connect the points with a solid line. That tells the reader that the boundary line, okay, the actual points on the line are part of the solution set, okay? And then we shade a half plane. And there's a couple of ways that we can kind of figure out which way to shade. So if you're dealing with something that's already been solved for y, as long as you have solved for y, the less than inequalities would tell us to shade below, and then the greater than inequalities would tell us to shade above. However, you always want to test a point. So we test a point. Okay, and that tells us how to graph just a single linear inequality in two variables. And we're going to do this twice on the same Cartesian plane. I will warn you, it gets a little messy. Okay, so be very neat, be very organized, be very particular about these because it can get messy kind of quick. Okay, So that's kind of the first step. We graph each inequality on the same coordinate plane, shade the region that satisfies each inequality. Okay, the solution, this is where I'm at right here. The solution is the overlapping region where all inequalities are true. So where does the shading overlap? Okay, every single ordered pair where the shading overlaps is an ordered pair that is part of the solution to the system of inequalities. Okay, and then you do have to be a little bit careful. Okay, you have to be careful where the two lines actually intersect. So where the two lines actually intersect, you have to put something there. You either have to indicate that that point is part of the solution or that point is not part of the solution, okay? And basically, if either of your inequality symbols is a strict inequality, meaning strictly less than, strictly greater than, if you have one of those two inequalities, we always want to use an open circle at that actual point of intersection, okay? And then if both inequalities have the or equals to, you would use a closed circle. Okay. So you do have to be a little bit cautious there when you graph these by hand. But other than that, you're just really plotting two linear inequalities in the same Cartesian plane and seeing where they overlap. Okay. So let's go ahead and look at some examples. So I will do these examples by hand, and then I'll also post a second video where you can see how to do these in Desmos. Okay. So example 2 here says graph each system of inequalities. All right. So luckily for us, the first inequality, we already have everything solved for y. So that makes it just a little tiny bit easier. Okay. So I'm going to do these in two different colors. All right. I think I'm going to do red and purple. Okay. So I'll do the first inequality in red and then the second inequality in purple. Okay. So for the first inequality, luckily it's already been solved for y. All I want to do now is figure out what is the slope, what is the y-intercept, and am I going to plot the points with a solid or a dotted line. Okay. So the slope here, once you have solved for y, the slope is the coefficient of x, okay? So the coefficient of x is 2, but I need to have a very distinct rise and run. I need to have a fraction with a numerator and a denominator. So I'm just going to write this as 2 over 1, okay? Now my y-intercept, once I have solved for y, is always the constant. So my y-intercept is -3, or I could think of it as the ordered pair 0, -3. And then I have a strict inequality. My inequality symbol is just plain old less than, okay? There's no or equals to component here. So we're definitely going to connect these points with a dotted line. And then because I'm already solved for y, the inequality symbol itself will kind of tell me which direction I'm going to shade. And because this says y is greater than, think greater than for shading above, but we will still test a point in just a minute. Okay, so let's go ahead and graph the line, and then we'll do just some really gentle shading. We don't want to get too crazy because, again, these get messy, okay? So we want to plot the y-intercept, which is -3. So at the origin, I don't go left or right, but I do go down 1, 2, 3. And then from there, I want to apply the slope. My slope is 2 over 1, so that tells me I can go up 2 and then to the right 1. So I'm going to go up 1, 2, to the right 1, up 1, 2, to the right 1, up 1, 2, to the right 1. I could also reverse both of those. Instead of going up, I could go down. Instead of going to the right, I could go to the left. So I could go down 1, 2, to the left 1, down 1, 2, to the left 1. I like to apply my slope 2 or 3 times if I have room, okay? And then we do want to connect these with a dotted line. That indicates to the reader that the actual points on the line, the boundary line, are not part of the solution. And then we think we're going to shade above, but let's go ahead and just test a point. Now, for me, I always test the origin if my line does not go through the origin, just because it's easy to plug in zeros. Okay, so I'm going to test the origin here. I'm going to plug in zeros into my original inequality for x and y. So y, which is 0, is greater than 2 times x, which is 0, minus 3. So we want to know, is 0 greater than? Well, 2 times 0 is 2. 2 minus 3 is -1. Is 0 greater than -1? And the answer would be yes. Okay? Gosh, I can't spell to save my life. There we go. Yes. Now that means the origin has to be part of my solution. That means it has to be part of the shaded region. And since the origin is right here, it's above the line, that tells me I'm going to go ahead and shade above the line. So I'm just going to put a couple of gentle lines there just to kind of remind myself, hey, I'm shading on top of this line. Okay? Now let's go back and do the line in purple, the second inequality. So for the second inequality, I have a slope of -1. It's already been solved for y, so the coefficient of x is my slope, and it is -1. But remember, we need a fraction. We need a rise over a run. We need a distinct fraction here. So I'm just going to put this -1 over 1, okay? The y-intercept is always the constant. So in this case, the constant is 6. That's my y-intercept. So the point 0, 6. I do not have a strict inequality. In this case, I have less than or equal to. So that tells me I need to connect these points with a solid line because the points on the line are part of the solution set. And then as long as you're solved for y, the inequality symbol will give you a hint about where you shade. This says y is less than. Think less than for shading below. And we'll test a point in just a bit. All right, so we want to plot the y-intercept, which at the origin, I don't go left or right. I just go up 6. So I go 1, 2, 3, 4, 5, 6. And then I want to apply my slope. My slope is -1. So I'm going to go down 1 and to the right 1. So down 1 to the right 1, down 1 to the right 1, down 1 to the right 1. Do that a few times. You could also, if you wanted to, go up 1 to the left 1, up 1 to the left 1. You're still on the same line. We want to connect with a solid line this time. Pretend it's perfectly straight. And we think we're going to shade below, but let's test a point. And again, I always test the origin unless my line goes through the origin. And my line does not go through the origin here. So I'm going to test 0, 0 in my original inequality. So anywhere I see an x or a y in the original inequality, I'm going to replace it with 0. So we want to know, is 0 less than or equal to -x, which is just 0, and then plus 6. So is 0 less than or equal to 6? 0 plus 6 is just 6. And the answer to that would be yes, 0 is less than 6. So that tells me the origin is part of the solution set for the purple line. So I would be shading below the purple line. So let's see where these like shadings are going to overlap, okay? So this point above the line and below here, these that are not part of the overlap are not going to be part of the solution set. So we just want to know where the purple and red shadings kind of cross each other. And they cross each other here. So I'm just going to darken this a little bit, make it a bit more obvious that this is the shading. Okay. And then you always want to just be really careful about the actual point of intersection where the two lines cross. And if you have, even if either of your inequalities is a strict inequality, meaning plain old less than, plain old greater than, you have to put an open circle at this point of intersection because it can't be part of the solution. So we would want to put a nice open circle right there to indicate that that point is not part of the solution set. And that's it. That's your solution. That's how you solve a system of linear inequalities. Okay. Like I said, it does get a little bit messy. Be very careful. If you could potentially find two colored pencils of different colors, that might be a nice way to go about this. That way you're shading where the overlap is going to be a bit more obvious. Okay. Now for part B, we have to do a bit more work here. For part B, the two inequalities have not been solved for y. So we've got to solve them both for y first. Okay. So let's start with the first inequality. So I have 3x plus y is less than 6. I want to solve that for y. So we're going to do this one in red. All right, all I need to do here is subtract 3x from both sides. Well, 3x minus 3x is 0. 0 plus y is y. So I get y is less than -3x plus 6. Okay? And in this case, my slope is -3 over 1. My y-intercept is 6. Okay? We want to connect these points with a dotted line because we have the strict inequality. And because when we solve for y, we get y is less than, think less than for shading below, but we'll test a point. All right, so let's go ahead and graph this one at the origin. I want to go up 1, 2, 3, 4, 5, 6. I don't go left or right, I just go up 6. And then from there, I need to apply my slope of -3. That means I go down 3 to the right 1. So down 1, 2, 3 over 1. Down 1, 2, 3 over 1. You could also, instead of going down 3, you could go up 3, but instead of going to the right, you would go to the left. So I could go up 1, 2, 3 to the left 1. And we want to connect these with a dotted line. And then let's test a point just to like double check our shading. Okay, so we're going to test again the origin. All right, so in the original inequality, anywhere you see x or y, plug in 0. So we get 3 times x, which is 0, plus y, which is 0, is less than 6. 3 times 0 is 0. 0 plus 0 is 0. 0 is less than 6 is true. So that tells me that I do shade below the line because the origin is below the line and the origin is part of the solution set. Okay? So let's look at the second line. We'll do it in purple. So for the second line, I have x plus 2y is greater than or equal to 2. Okay? I want to subtract y first. So I subtract y, or subtract y. Please forgive me. Subtract x. We want to subtract x first. X minus x is 0. 0 plus 2y is 2y, which is greater than or equal to negative x plus 2. All right. I now want to divide all three of my terms by the coefficient of y. I need to undo that multiplication of 2 and y. We do that with division. So I divide everything by 2. 2 divided by 2 is just 1. 1 times y is y. So we have y is greater than, and then negative 1x divided by 2 is negative 1/2 x. And then 2 divided by 2 is just 1. So this is the inequality that we're graphing. It's the same inequality that we started with. It's just in a format that's easier to graph. Okay? So once you solve for y, the coefficient of x is your slope. So our slope is negative 1/2. The constant is your y-intercept. So my y-intercept is positive 1. I do not have a strict inequality. I have an or equals to inequality. So I want to connect my points with a solid line. And after solving for y, we have y is greater than, think greater than for shading above. But we'll test a point. Okay, so let's see. We want to plot 1 for the y-intercept. So at the origin, I don't go left or right. I just go up 1. And then I want to go down 1 to the right 2, down 1 to the right 2, down 1 to the right 2. I could go up 1, but then I have to go to the left 2. All right, we want to connect these with a solid line, pretend it's perfect. And then we think we're going to shade above, but we're definitely going to test a point. So we're going to test 0, 0. It looks like our line is really close to the origin, but it officially does not go through the origin, so we can test that. So anywhere I see an x or a y in the original inequality, I'm going to replace it with 0. So I get 0 plus 2 times 0 is greater than or equal to 2. Well, 0 plus 2 times 0 is just 0. And then we have to ask ourselves, is 0 greater than or equal to 2? And the answer here would be no, okay? This is not a true statement. This is a false statement. So that tells me that the origin is not part of the shaded region for the purple line, which tells me I don't shade the half plane that contains the origin. I shade the other half plane. So I would shade above the line, okay? So let's see where the red and purple lines overlap. That's going to be our solution, okay? So we do not have overlapping here, 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 or here. We do have overlapping in this kind of like upper left-hand corner. So let me fix that a little bit. We are going to shade this right here. Now, the issue is the actual point where the two lines intersect, okay? If either of your inequalities is a strict inequality, meaning there is not the or equals to, then you cannot include that point where the two lines intersect, and that's the issue we have here. So we would put an open circle at that point right there. Let's see if I can erase it. Whoops, I didn't mean to erase the whole line. There we have it. So we put an open circle at that point where the two lines intersect, okay? It's kind of a long video, but 2 more examples. Okay, so for part C, luckily the first inequality is in slope-intercept form and the second inequality is a vertical line, so this one's going to be a little bit quicker. All right, so for the first inequality, let's go red. All right, we've already been solved for y, so we can jump straight to the slope and the y-intercept. The slope is the coefficient of x, which is just 1, so I'm going to write that as 1 over 1. The y-intercept is the constant, which is negative 1, and we do have a strict inequality, so we want to connect with a dotted line. And then it says here that we have y is greater than, so that would indicate that we're going to shade above, but we can test a point in just a minute. Okay, so let's plot our y-intercept. At the origin, we don't go left or right, we just go down 1. And then we want to apply our slope, which is positive 1 over 1. So we go up 1 to the right 1. So up 1 to the right 1, do that a few times. Instead of going up and to the right, we could go down, but then we'd have to go to the left. So down 1 to the left 1, do that a few times, and connect with a dotted line. All right, we do need to test a point. So let's test the origin. Even though it looks like our line is going through the origin, it's not, I promise. So we can test the origin here. All right. So let's see. We go back to the original inequality. Anywhere we see an x or a y, we plug in a 0. So we get 0 is greater than 0 minus 1. We're up here. So is 0 greater than negative 1? Well, yeah, it is. So 0 is greater than negative 1. So this is true, which tells me that we do shade the half plane that contains the origin. So we would shade above this line. Okay? So now let's do the other line in purple. So in purple, we have x is greater than 5. So anytime you're dealing with equations or inequalities in two variables, if one of the variables is missing, solve for the variable that you do have. We've already been solved for x here. Okay, so with only an x, that means we have to touch the x-axis, but we cannot touch the y-axis. The only way for that to happen is if this line is vertical. Okay, so this line is vertical with an x-intercept of positive 5. So when you have just one variable, solve for that variable, and the value you get when you solve becomes the y or the x-intercept, in this case, the x-intercept. So at the origin, we go to the right 1, 2, 3, 4, 5. That's our y-intercept, or our x-intercept, excuse me. Okay, we want a vertical line through here, and we do want it to be dotted. Okay, we have a strict inequality here, so we can't have a solid line. The points on the actual line are not part of the solution. So we want a dotted line. And then this says x is greater than 5, which would tell us to shade to the right, to shade above. Okay. So let's figure out where the shading overlaps. It does not overlap here, 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 or any of these. It overlaps in this upper, like kind of right-hand corner. So our shading is right here. This is our solution. And we have two strict inequalities, which means this point right here where the two lines intersect is not part of the solution set. So there you have it. All right. Now, finally, for the last example, luckily the two lines have been solved for y, so that's helpful. We can go ahead and get both of these graphed, so I'll use red and purple again. So for the red line, we have a slope of 2, okay, the coefficient of x, as long as you've been solved for y, the coefficient of x is your slope, so I'm going to write it as 2 over 1. My y-intercept is negative 3. I do not have a strict inequality. I have an or equals to inequality. So I am going to connect these points with a solid line. I think I'm going to shade above because we have greater than or equal, but we'll test a point. Okay. So at the origin, we don't go left or right. We just go down 1, 2, 3. And then we apply our slope. Since our slope is positive 2, we go up 2 to the right 1. So up 1, 2 to the right 1, 1, 2 to the right 1. We could also go down 2, but then we'd have to go to the left 1. So I could go down 1, 2 to the left 1, down 1, 2 to the left 1. And we want to connect with a solid line. And we think we're going to shade above, but we'll test the origin again. Remember, you can always test the origin as long as your line does not go through the origin, and we don't. We have a y-intercept that's not 0, so we're good here. So to the original origin, anywhere we see an x, or to the original origin, to the original inequality, anywhere we see an x or a y, replace it with 0. So I would get 0 is greater than or equal to 2 times 0 minus 3. So is 0 greater than or equal to, well, 2 times 0 is 0. 0 minus 3 is negative 3. Is 0 greater than or equal to negative 3? And the answer to that would be yes. So the origin is part of the shading. So we do shade on top of the line. Okay. Now in purple, we'll do the second line. Okay. So in purple, we have this equation or this inequality right here. The slope for the second inequality is the same. It's 2 over 1. So if two lines have the same slope and different y-intercepts, they end up being parallel. So let's see what that's going to look like here. So we have a slope of 2, so we have the same slope. We have a y-intercept of 1, different y-intercepts. So these two lines, when we graph them, are going to be parallel, but we still have to finish this. We can't just jump and say there's no solution because we have to see where shading overlaps, okay? So let's see, we've got our slope, our y-intercept. We're going to connect the points with a solid line. And then we have y is less than or equal to 2x plus 1. I think we're going to shade below, but we always test a point just to be super careful. So we can test the origin again. We'll test that in just a second. I guess I'll go ahead and get my line graphed first. So let's see. We want to plot 1 on the y-axis. So at the origin, we don't go left or right. We just go up 1. And then our slope, we go up 2 to the right 1, up 2 to the right 1. We could also go down 2 to the left 1, down 2 to the left 1, connect with a solid line. So you can see these two lines are certainly parallel, okay, but we have to see where the shading is, okay? So for the purple line, we think we're going to shade below, okay? So we want to test the origin. So anywhere we see an X or a Y in that second inequality, we replace it with 0. So 0 is less than or equal to 2 times 0 plus 1. 0 is less than or equal to 0 plus 1. Is 0 less than or equal to 1? Yes, that would be true. So this tells me that we do shade below the line. And then for the red one, we ended up shading above the red line. So this right here is where our shading would overlap. And we don't have a point where the two lines intersect, so we don't have to worry about that point of intersection here. We just know that any points on either of the line plus the shading in between the two lines is the solution to this inequality. Okay, so that is graphing systems of linear inequalities in two variables. Make sure you know how to just graph a single inequality in two variables first. Practice that before you dive into the systems. Otherwise, the systems are going to be extra hard. So just make sure you understand that you plot or you graph both inequalities on the same Cartesian plane, and you look to see ultimately where the shading overlaps.